Good afternoon again. My name is Lisa Matthews with EPA's Office of Research and Development. Thank you for joining us for today's Tools and Resources webinar, which is going to highlight EPA's National Stormwater Calculator and how the Stormwater Calculator has been applied in the Great Lakes. We have 3 different case studies that are going to be presented today. If you have a question during the webinar, please type it into the chat pod, and once the presentation ends, we will go through as many of those questions as time allows. We will be posting the slides from today on the EPA research website, and Aaron has typed that web address into the chat pod. And I'm going to go ahead and introduce our presenters today. We have Carly McMorrow, who is an ORISE Research Participant from the EPA's Great Lakes National Program Office. Chris Hartman, a Stormwater Technical Specialist from the Northeast Ohio Regional Sewer District. And Frank Marsik, a Research Scientist with the University of Michigan's Great Lakes Integrated Sciences and Assessment Program. I'm going to be turning this over to Jason Bernagros with EPA's ORD Center for Environmental Solutions and Emergency Response. Jason is in our Stormwater Management branch, and we're going to be muting all the lines before Jason speaks to cut down on background noise during the presentation. So thank you all for joining us today, and Jason, I'll turn it over to you.
The leader has muted your line. To unmute your line, press #6.
To view this webinar today on applications of the National Stormwater Calculator in the Great Lakes region. I'm assuming many of you are familiar with the National Stormwater Calculator. It has been available for public use since 2013, and it's used for screening level analyses of urban stormwater runoff for small development or construction sites. You can use it anywhere in the United States, including the Virgin Islands, Puerto Rico, Hawaii, and Alaska. And it's used by landscape architects, urban planners, civil engineers, and it's a very user-friendly tool that allows you to look at urban runoff conditions using different scenarios, with the most commonly used low-impact development or green stormwater infrastructure controls under both historical and projected climate change scenarios. So as Lisa had mentioned, we are going to go through 3 case studies of how the National Stormwater Calculator is being used in the Great Lakes region. And our partners are going to discuss EPA's Great Lakes Restoration Initiative, so a regional programmatic view of how the calculator is being used and promoted. And then next, the Northeast Ohio Regional Sewer District's Green Infrastructure Grants Program is going to discuss how the tool is used for reviewing green infrastructure grant applications. And then lastly, the University of Michigan's Great Lakes Integrated Sciences and Assessments Program is going to discuss how they've used the calculator for tribal capacity building, looking at how it can be used to manage runoff from extreme storm events. And I just want to say, while we won't be going through a lot of the background and basics of the National Stormwater Calculator today, if you are interested, you can check an archived webinar from the Tools and Resources webinar website. It is from August 23rd of 2017, in case you'd like some additional information. And with that, I will hand over to Carly.
right. Thank you, Jason. Thank you, Jason. Good afternoon, everyone. My name is Carly McMorrow, and I am an ORISE Research Participant in the Great Lakes National Program Office, housed in the EPA Region 5 offices in Chicago. I'll be presenting today on how the National Stormwater Calculator is utilized by the Great Lakes Restoration Initiative. The Great Lakes Restoration Initiative accelerates efforts to protect and restore the largest system of fresh surface water in the world, and is committed to creating a new standard of care that will leave the Great Lakes better for the next generation. Since 2010, the multi-agency GLRI has provided funding to 16 federal organizations to strategically target the biggest threats to the Great Lakes ecosystem. GLRI provides funding beyond base funding to accelerate progress toward achieving long-term goals. It should be noted that GLRI cannot be used to fund enforcement actions or other required efforts. We also coordinate closely with states and tribes to ensure that we take their priorities into consideration. Action Plan 3 was developed with input from states, tribes, local governments, universities, and NGOs. It outlines the priorities and goals for GLRI specifically for the fiscal years 2020 to 2024, and it's working towards accelerating environmental progress in 5 focus areas, and those focus areas would be 1, toxic substances and areas of concern, 2, invasive species, 3, non-point source pollution impacts on nearshore health, 4, habitats and species, and 5, foundations for future restoration actions. GLRI Action Plan 3 outlines the next phase of work on Great Lakes environmental problems, and it lays out the necessary steps to get us closer to the day when we will be able to achieve our long-term goals for the Great Lakes. GLRI is an ecosystem-based program, and we work across 3 regions, parts of 8 Great Lakes states, and we're committed to the Great Lakes Water Quality Agreement between the U.S. and Canada. So the Stormwater Calculator comes into play mostly in Focus Area 3, the non-point source pollution impacts on nearshore health. So in addition to the EPA, we also work primarily with the Forest Service, Fish and Wildlife Service, the U.S. Geological Survey, the Bureau of Indian Affairs, and the Army Corps within Focus Area 3. And GLRI federal agencies and their partners are committed to accelerating implementation of green infrastructure practices to infiltrate stormwater runoff and implementing watershed management projects in urban and rural communities to reduce runoff and erosion under Focus Area 3. And GLRI federal agencies and their partners will continue to encourage and accelerate implementation of green infrastructure projects to reduce the impacts of polluted runoff on nearshore water quality. And then GLRI funding for fiscal year 19 was $300 million, with about $4.5 million on average going towards the green infrastructure grants. And under these grants, EPA's National Stormwater Calculator, or an equivalent formula, is required to calculate the gallons of stormwater runoff reduction. So just a bit on how the stormwater gallons are used as a metric. So this measure tracks the estimated numbers of gallons in millions of untreated stormwater captured or treated under GLRI-funded projects. So for example, if an agency is reporting 10 million gallons, they would just enter the number 10. Estimates of stormwater captured or treated due to the implementation of GLRI-funded projects in urban, rural, or mixed land cover watersheds are acceptable results to count for this measure. Some unacceptable results for this measure would include results from projects implemented without the expenditure of GLRI funds, or projections calculated using an unapproved calculation method. And it should be noted too that these gallons will be estimated for the reporting period in which they can first be identified for the project. The EPA then reports the progress that's made through the GLRI to Congress and the President. And if you take a look at the image here, you'll see under 3.2.1 estimated gallons in millions of untreated stormwater runoff captured or treated. We've outlined our targets for the coming fiscal years through 2024. And while these targets are ambitious, we're hoping to be able to meet all of those goals by the end of those fiscal years. So just to go over some of the take-home messages from the GLRI case study, GLRI was created to protect and restore the largest system of fresh surface water in the world. GLRI federal agencies will continue to use GLRI resources to strategically target the biggest threats to the Great Lakes ecosystems. In Focus Area 3, Objective 3.2, to reduce untreated stormwater runoff, is committed to accelerate implementation of green infrastructure practices, to infiltrate stormwater runoff, and to implement watershed management projects in urban and rural communities to reduce runoff and erosion. And the Stormwater Calculator was used to estimate the annual amount of rainwater and frequency of runoff from a specific site, which we then report to Congress as environmental accomplishments. And then my contact information is listed below, along with my mentor and supervisor, Danielle Green. So if any questions should arise later, please don't hesitate to reach out to one of us. I should also mention, too, that if you'd like to learn anything more about the Great Lakes Restoration Initiative, you can visit the website at glri.us. And that's a good way to stay informed about all of the work that we're doing within the Great Lakes. So thank you, and I will pass it on to Christopher now.
Thank you, Carly. Good afternoon, everybody. This is Chris Hartman. I'm a Stormwater Technical Specialist with the Northeast Ohio Regional Sewer District. And I just wanted to give you a quick overview of what the sewer district is all about. So we provide stormwater and sanitary services to 62 communities within the greater Cleveland metropolitan area. We have 1 million customers. We treat a lot of gallons of stormwater and wastewater runoff through our 3 wastewater treatment plants that we operate within our service area. And we also have a regional stormwater management program of which we have nearly 500 miles of stream and culverted channels that we oversee maintenance of to ensure proper conveyance of flow. In addition to that, we perform water quality monitoring throughout the service area, and we also are highly involved with Lake Erie beach monitoring and maintenance along the shoreline. So we have a green infrastructure policy, and I wanted to touch on this simply because it ties right into why and how we use the Stormwater Calculator. So the green infrastructure policy, through our own project and through private development, we advocate for cost-effective GI technologies to be utilized when possible. Obviously, that purpose is to protect and preserve and enhance the natural hydrologic function of the stormwater. And we certainly try to maximize any co-benefits that can be achieved anytime that we do our own projects to make sure that they are enhance the communities that we place our projects within. Now, this is all achieved through 5 key program areas. Our capital improvement and operation and maintenance program, which is the bulk of our work. We have a member community infrastructure program where we provide funding for our member communities to perform infrastructure of sanitary and stormwater improvements and enhancements. The state of Ohio has a water resources restoration sponsorship program, and this is where when we get a loan from the state of Ohio to do a project, the interest of that loan is made available to outside parties to perform and create environmental projects that enhance water quality. And we will sponsor the projects that want that funding as necessary. And then we have our own code of regulations that regulate stormwater runoff within the combined and separate sewer areas in our service area in conjunction with our service or our member communities. But today's discussion is going to focus on the Green Infrastructure Grants program that we have and how we use the calculator to benefit that program. So the Green Infrastructure Grants program is a funding source that's open to member communities, the 62 communities I mentioned earlier, governmental entities, nonprofit organizations, and even private property owners that work in cooperation with any of the above. The goal overall is to remove stormwater from the combined sewer system. Only properties that are located within our combined sewer area are eligible. And in the long run, anybody who is awarded a contract or a grant, I should say, they maintain the long-term ownership of the property and the GI features that are constructed as part of the grant, and they also are responsible for the long-term maintenance of those practices. So on the right side of the screen there, you can see where it's a screenshot of our green infrastructure story map from our website, and it's a good way to see the types of projects that we have funded with this program. It gives you a little bit of information about each one. So we have about $2 million a year that we have available to us to loan out as grants for anywhere between 8 and 10 projects per year. The maximum request is set at $250,000 per application, and since 2016 we've awarded over $8 million in projects. So again, the goal being in the combined sewer system service area is to ultimately increase the resiliency of that system that's overtaxed every time it rains by decreasing the volume of stormwater runoff that is conveyed to that system. We're simply trying to soak it up or harvest it and reuse it for another purpose for the most part. So the projects that we have constructed and worked with applicants on and that are planned for this upcoming year total an estimated annual reduction of runoff of about 26 million gallons. And those numbers are directly result from the Stormwater Calculator effort that we have with the program. So there's 3 main reasons why we like the Stormwater Calculator and why we use it for this grant application process. Our goal simply is to make sure that we know how many gallons are captured on a property when you add green infrastructure components to it. So we look at the pre-development versus post-development scenarios and see what the difference is in runoff by adding those features. There are lots of data that's typically needed to do this kind of analysis, and the applicants have varying skill sets when it comes to knowing how to run these types of models. So we wanted something that was user-friendly, that for the most part with a little training folks could pick up on and use and get us the numbers we needed for the applications. And certainly we wanted something consistent. We need to compare. Although we award 8 to 10 grants per year, we have anywhere from 10 to 15 applications per year that we have to rank and decide who we're going to fund. So being able to compare everything apples to apples is important. So all of these issues are addressed by using the Stormwater Calculator. So here's a typical site plan that we will see from a given application. We start with a existing conditions situation. This is a parking lot that was funded at one time a few years ago. The drainage on it goes from right to left, and you can see that there's no GI features whatsoever on the property. And the applications typically show us the retrofit of the features of the property. And in this case, they added 5 bioretention cells, maintaining the existing drainage patterns, but certainly reconfiguring the parking bays on the property as well. But now we were able to capture the entire parking lot runoff and route it to a green infrastructure practice. And so that represents a very typical project that we see through this grant. And this parking lot was about 2.5 acres in size. So when we see these things, what we're looking at here, I can hope this arrow works, the baseline scenario represents the existing conditions. And if you're familiar with the calculator, this terminology will make sense to you more so. But the baseline scenario is the existing conditions. The current scenario is what is it with green infrastructure practices applied. And you can see I've highlighted some of the key information here, how the land use, which is some of the data input you need for the calculator, how that changes by adding a green infrastructure. Not much in this case, but somewhat. But more importantly, down at the bottom here, the addition of the actual green infrastructure practices. The existing conditions, we had nothing. The proposed conditions, we have a number of rain gardens that are going to address the runoff from the site. So what we get from that is this number right here, the average annual runoff. When you run these model scenarios, what we focus on is how much rain is coming and a runoff is happening, and how much is running off the property in existing conditions and, of course, in the proposed conditions with the GI features. And that difference is what we are interested in. And we simply convert that to the gallons per year using this equation right here. Again, taking the difference between the two scenarios and doing the correct calculations for that scenario. So the Stormwater Calculator is an excellent resource, we believe. It allows the user to run various scenarios and to kind of play with their property, if you will, by inputting different types of GI features to see where the best results are to hit the goals that they want. So not all the applicants have a design engineer on staff or hired at this point in the game when they submit their application. So it's important that they be able to utilize this resource and understand how it works to their benefit. So to help with that, we offer training at various stages of each year's grant cycle. The first would be the hosting of a pre-proposal workshop. This is where we invite any interested party to a half-day workshop to explain the whole grant application process and how to utilize this tool. We do, once we submit the RFP for that year's grant, we will certainly provide one-on-one consultations with applicants and be available to answer questions as they try to run these models to make sure that they have accurate numbers. So here is an example of the type of information that we review during the pre-proposal workshop. If you're familiar with the layout of the calculator, this will be familiar to you. There are a number of lid controls, and you can see them right here, that are able to be selected to run these different scenarios. So we review each one of those in great detail. and then we go to the detail data input area and explain what all this information here means as far as a design of a practice, so that they are familiar with what data is required to make sure this model is accurate. And then we review also each of the modules, and the modules are the tabs at the top of the screenshot here that I'm pointing at. And here's a list of them here as well on the left side. But we review each one of those modules so they understand what those mean and what type of information is looked at. But more importantly, certain modules we don't really have a lot of interest in at this point for an application stage. For example, the climate change. And we tell folks, for consistency's sake between applications of what data to input in this situation. For example, the climate change one is we simply want them to select no change and to select the near-term option for that. And so every application does that for consistency. And this screen here is really the end result that we want to make sure that they understand. So here is a particular hypothetical site where we provided them existing conditions, developed conditions without lid controls or GI features, and then the same site with one green infrastructure control measure applied, and then the same site with multiple lid controls applied to the scenario out there. And the focus are the highlighted lines. We simply want them to understand you're going to get a result for each one of these scenarios that shows the average annual runoff. Existing conditions will typically be less than your proposed conditions, but as you run these varying scenarios and what I like to say play with the model, you can see how that gap is closed as far as the amount of runoff that comes off the site annually. And again, that's the key number that we're focusing on. So we also at that time provide helpful hints so that we can maximize consistency. And this would be things like understanding the terminology of the model. Bioretention is a very popular practice that we fund, but you won't find the word bioretention anywhere in the model. So we explain to folks that our opinion of the best fit of the options available as lid controls are street planters in that case. So that would be the one they would want to use when they run their model. And certainly we want to make sure they understand when they're inputting the percentages of impervious and pervious footprints on their study area of how to account for permeable pavements and green roofs as impervious and the footprints of some of the more vegetated practices as pervious footprints and their percentages. And in the end, this slide kind of shows you what, on the left here, this is a screenshot from one of the actual applications we have. Our goal is to double check their numbers when they provide us their annual average runoff in gallons they save per year. So right here, you can see where they provided us the fact that they are proposing permeable pavers, 5,300 square foot field of permeable pavers with a drainage area of 0.34 acres. So we use those numbers and we put those in what we call, obviously, the applicant's information and get their numbers, their results of reductions of gallons per year. But then we use their information and their narrative to rerun that model with our interpretations of what they're really trying to do and see if we agree with their assumptions or not. And sometimes we agree, and you can see the difference between our assessment and their assessment is almost identical on this case. So that would be one application that we agreed quite well with. Sometimes we think that they actually capture more. Maybe they underestimated something or made an incorrect assumption. And sometimes they overestimate, and our numbers come out lower than their numbers. But we are confident that as far as the ranking of the applications, we end up using our numbers for the final results. So some of the challenges we have with using the calculator and some of its limitations need to be highlighted here. Again, terminology isn't consistent with what the GI industry uses, the best example being bioretention. So folks who use the calculator need to understand what the best fit lid control would be for their type of practice that they're proposing to use. The model doesn't allow you to really easily do treatment trains and to account for the benefits of treatment trains, so you have to be somewhat creative with that. And occasionally we get a very unique type of proprietary practice, perhaps, that doesn't fit the model at all. And sometimes we work with the applicants to make sure that they utilize the right model and right lid control, or perhaps we advise them to try a different model altogether to give us the numbers that we want. So some take-home messages with this. The input and the output, we believe, is very user-friendly. So that's the biggest strength of the model. There's no need for a design engineer to run this model. Anybody with a little bit of training is able to run it and to understand it. We certainly do improve our consistency of analysis between the stormwater control measures, which allows us to do that apples-to-apples comparison between the applicants. And ultimately, we're achieving our goal, making sure that we understand what how many annual gallons are captured by the proposed GI features on any given property between the pre-development scenario and the post-development runoff scenario. So that concludes my talk, and I'm going to hand it over to Frank now, and he'll let you know what he has. Thank you.
All right, thank you very much, Chris. So my name is Frank Marsik. I'm at the University of Michigan in the Climate and Space Sciences and Engineering Department, but I'm also part of the Great Lakes Integrated Sciences and Assessments program here at the University of Michigan. GLEAS is actually a joint entity between the University of Michigan and Michigan State University. We are one of 10 ORISEs, which are Regional Integrated Sciences and Assessments groups. And our goal, we view ourselves as a boundary organization, basically trying to take the climate research and data that is out there, create a series of products that can then be used by various climate services or directly with the partners that we might be working with. Obviously, some of that climate research data, when you start looking at long-term projections, can be quite complex, and we try to present it in a way that is more user-friendly for those that we are working with. The particular work I'm going to be talking about today, actually the motivation for that was a number of years ago. The Bad River Band of Lake Superior, Chippewa in northern Wisconsin experienced a very heavy extreme rainfall event on the 11th of July back in 2016. There were a series of thunderstorms that moved over the exact same area, producing on the order of 8 to 10 inches of rain, mostly within an 8-hour period, though the event actually lasted longer than that, and they experienced a severe flooding during the days following that. The pictures on the right you can see kind of provide an example of some of the flooding. You can see what appears to be like a church building or some type of structure there, and then also on the bottom you can see the roadways that had been washed away. And so a state of emergency was declared for the tribal lands both by the Bad River Band Tribal Council and the state of Wisconsin. And so we received funding from the Great Lakes, or excuse me, the Graham Sustainability Institute, as the tribes had reached out to us following this, the tribes of Michigan, because they had seen the damage that was incurred by the Bad River Band, and they were concerned about whether or not they might be susceptible to such an extreme rainfall event, and were curious as to what are some of the tools that were available that they might be able to try to prepare for such an event. So the Intertribal Council of Michigan, which is an umbrella organization that provides services to the tribes within the state of Michigan, reached out to us and indicated that the tribes had expressed this concern and wondered if GLESA would be able to help provide a workshop that might provide information on some of the tools that were available. So we worked closely, Maria Carmen Lemos and myself, with Robin Clark from the Intertribal Council of Michigan, and to host this event. It was actually hosted at the Bay Mills Indian community, so we are very grateful for those folks. And you can see a list of the participating tribes in that particular workshop. I'm not going to go through and list them all. Like I said, the goals, there were multiple goals of the workshop. One is that the Intertribal Council of Michigan had already worked with the various federally recognized tribes in the state of Michigan to come up with a vulnerability assessment in the previous couple of years. And so one of the things that we wanted to do was provide the tribal nations with that opportunity to share some of their climate adaptation goals and the progress they had made in the years following that assessment that was performed. And then also, as I mentioned, we wanted the tribes to be able to, or the tribes had asked us if we would be able to provide them with just some overview of the different types of tools that might be available to them to try to prepare for some extreme rainfall events. So we provided a number of tools. One of them involves scenario planning, which is one of the approaches we use as part of GLESA. Here's an example of one of the products that we provide. One of the things that we're seeing in the Great Lakes region in terms of our changing climate since 1951, between 51 and 2017, is an overall increase in precipitation of about 14%, and the 1% heaviest events each year have been seeing their amounts increasing over that time as well. And so the approach that we often use is to not simply say what happens if there is more rainfall. We take a look and say, well, what if there is an extreme precipitation event during a particular dry period? Or what if there is an extreme precipitation event during a wet period? Or if that rain is falling over bare, frozen ground? So we worked with the tribes in understanding some of these scenarios that we think would be beneficial for them to consider when they're developing their programs. And so in addition to the scenario planning, we looked at a couple of different tools, one being the Game of Floods that was developed by Marin County, looking at making some climate adaptation planning decisions during coastal flooding. While we weren't necessarily going to expect to see those types of events quite as much in the Great Lakes region, certainly the thought process going through was a valuable exercise. And then one of the other things that we did was indeed talk about EPA's National Stormwater Calculator. One of the take-homes from that workshop was that the representatives felt that the Stormwater Calculator really did have the potential to provide a valuable tool for understanding what is the potential frequency of these extreme events and what the impacts might be in terms of stormwater runoff. But they also noted that they were concerned about the fact of their inability to maybe direct resources toward such efforts, both in terms of the human personnel component and also financial. Many of these natural resources staffs within tribal nation governments are quite small, and during the summer and fall seasons, they're very active out of doors, and there is some limited time that they have to direct toward these efforts. So as a result of that, we went back to the Graham Sustainability Institute and sought additional funding to work with a number of the tribes to try to perform at least some base estimate of stormwater runoff. Chris mentioned kind of this being a screening level model, and that's the approach that we took to take those tribes that were most concerned about wanting to address this situation in the near term and doing some basic assessment for them that they would then be able to carry forward after working with us on, or working together on this effort. So this was a smaller number of tribes. We worked with the Little Traverse Bay bands of Odawa Indians, Grand Traverse Band of Ottawa and Chippewa Indians, the Saginaw Chippewa Indian Tribe, and the Keweenaw Bay Indian community. One thing of note that was nice on that I thought through this process was that I had a summer research student from the Keweenaw Bay Indian community who worked with me on the project and the assessment for their tribal land. So that was nice that someone within the community worked so closely on that project. Now, given the consideration of the sovereignty of the tribal nations, I'm choosing not to try or providing any specific site-based examples. And additionally, for each of the tribal nations that we worked with, we were looking at probably 3 to 4 different sites per tribe, so that would take some time to go through. What I thought I would do instead is just kind of give you an overview of what we were trying to do with each of the tribes. So in essence, we decided to do just a basic climate assessment, a baseline, as Chris called it, without any of the low-impact development controls that are possible. We looked at just what I'm calling standard soils, just a traditional soils that were assessed with the Stormwater Calculator, and then we looked at those standard soils as well with extreme precipitation events and looked at what the runoff might look like for those. And then in the northern Great Lakes region in general, but particularly as you go farther north, throughout part of the year, the soils are often frozen or they're often snow-covered. And so one of the things that's really nice about the Stormwater Calculator is the ability to change the values of infiltration for a particular site that you're doing. And so that is one of the things we did, and I'll show that briefly. In addition, we looked at what the current climate conditions were, and we then moved from our baseline to look at what possible benefits from reducing stormwater, that the runoff that the tribes could do using some of the low impact development controls. And then finally, we've also performed future climate assessments, both with and without those lid controls, and both for the short-term climate change and long-term climate change as well. The tribal communities, many of them are tribal nations, are on particular reserved lands that were negotiated with the federal government, and so one of their concerns is that as climate conditions are changing, they need to be able to understand how that's going to impact their natural resources and on their tribal lands, and so looking at these climate change conditions is of great benefit to them. So here's just an example of why one would want to go the extent of looking at how ground cover is changing through the course of the year. On the right side is the baseline. Looking at, in this particular location, the annual rainfall was 32.1 inches. And you can see that one of the nice things, as Chris showed with the Stormwater Calculator, is that you can look at the relative amounts of runoff, infiltration, and evaporation. On the left-hand side was a situation where we went into the literature and we found estimated values for the infiltration for frozen soils. And so given the flexibility of the Stormwater Calculator to not only use local soil information, but also to modify that, we went ahead and modified it for the literature information regarding what the infiltration would be for frozen soils. And as you can see, when one considered that, you had a significant increase in the amount of runoff during those seasons. And so for tribal communities, or really any communities, that flexibility of the Stormwater Calculator to change the expected infiltration rates or other parameters is very helpful. So one of the groups that we were working with, as I mentioned, was the Little Traverse Bay Bands of Odawa Indians, and we spoke with them recently about what they're doing using the information that we did provide to them and with them. And one of the things that they talked about is that the assessment was able to provide them with information for an area of concern that was typically a problem during spring flooding when the soils were frozen, when there was snow on the ground. However, while this area of concern is on the tribal reserved lands, they do not currently own this property, and therefore, even though they recognize a problem, they can't necessarily do anything with it unilaterally. However, getting this information through this assessment and using the tool to look further, they can use this information should they acquire property in that area in the future, and also use that information working with some of the local communities to address this situation. After the project was done, we continued some post-project conversations, and it was indicated that they have use that information to start thinking about other sites on their reserved lands that they might want to try to do an assessment with. They're trying to develop tribal stormwater best management practices, and so certainly the Stormwater Calculator is going to allow them to do baseline assessments, as we said, vary based on season, and then also look at what the potential impact of various low-impact development controls might be. The other thing that they're going to be using the Stormwater Calculator for is that they'll be able to model results. Chris was noting that various people coming to them looking to receive funding for various projects can use the Stormwater Calculator, and certainly that is one of the things that the Little Traverse Bay bands of Odawa Indians are planning to do. Also, they're indicating that they found that given the graphics that are generated by the Stormwater Calculator, they feel that it's going to be very beneficial in terms of community outreach events and education events as well. And so lastly, kind of some take-home messages from the work that we've been doing. Again, just to emphasize that many tribal natural resources departments are very resource limited, both in terms of personnel and budgets. And so the Stormwater Calculator provides a very good time and cost savings. The embedded data sets that are within the Stormwater Calculator make it easy for them and other small communities not having to search the internet or other data sources to try to find information on the meteorology, the soils, the topography, and the cost structure. That's certainly one of the things that was beneficial to the tribes is the various scenarios that we did look at with them. They were able to see what the different costs were for some of these things like the rain gardens versus impermeable pavement or permeable pavement. And the other nice thing that the Stormwater Calculator allows the tribal communities to do is to blend the information they achieve or they obtain with the Stormwater Calculator with traditional ecological knowledge or place-based knowledge. These tribal nations have been across the Great Lakes for thousands of years. They've witnessed what some of the impacts of extreme events are, and they can rely not only on the numerical results from the Stormwater Calculator, but based on their traditional history, they can go back and understand how events such as that did impact their community. And as we mentioned, the calculator is accepted as a tool to build cases in proposal submissions. As an example, the National Fish and Wildlife Foundation allows the use of the Stormwater Calculator as an acceptable metric when providing or when writing proposals. So as far as acknowledgments, I just wanted to thank the Graham Sustainability Institute at the University of Michigan providing funding for both the workshop and the related Stormwater Calculator project. I want to thank the Intertribal Council of Michigan for the development and facilitation of our workshop and the project. And finally, last and definitely not least, I want to thank our partner Great Lakes Tribal Nations for their trust in working with us in our collaborations with GLESA and also for sharing the gifts of their knowledge. And that is all I have.